He got killed.
As I've been saying a couple times at this conference, it's so directed to radiation. You know, this conference has done so much with radiation, but there's other things. Radiation is more of an external thing. It comes, what measures comes in, what comes out. There's also internal stuff. There's variations of evaporation and rainfall. And there's also what I consider the primary driver of climate change, if you discount the orbital forces, is the salt oscillator. The oceans build up salt in certain ways, and you have different subsidence, and the MOC, or the meridional ocean circulation, changes, and that is the primary driver of climate change. So, I'm sort of saying it here, it's radiation, 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 not the whole story. There's also these other evaporation and things. I won't talk about that. There isn't time. But hey, how did I get here? Did someone get me out of here? Oh, thank you. Okay, well now, here's the radiation buffer. We have the estimates on crude. We've got about 342 watts per square meter coming in, the albedo. And of this, about half comes down to the surface. And of this half, about half of that, in other words, there's all this energy forcing on the surface to warm it, and the cooling processes are here. You've got about half of them are evaporation that cools the surface. And then we have sensible heat and ion radiation going back. Now, these are large terms compared with the CO2. We're right up now, the best estimates were a little more than a third of the way to doubling CO2 from the start of the Industrial Revolution. Now, the whole theory has been this is a driving mechanism. You see, you have all these things going on, all these terms. This can vary. Solar absorption can be a little bit more. The rain can go up and down. All these things can go on. We know in reality, but they're disregarded. They're all constant. So this little bit here drives the whole damn system. Or you can go to this, the Maunder minimum, and all these little things are tweaking this little thing less than 1 meter per second, or watts per square meter, and this is driving the whole system. It's we're just thinking wrong on this thing. It's we're not getting it through fundamentals, in my view. Now, if we double CO2, the estimates are about 3.7 watts per square meter will come in and warm. So we'll have additional warming of this of about this. If this would be parceled out, as it is now with the total system, you would have the rainfall increasing about a little over 2%. This would go to 1.8. These other values would go up, and you'd balance the 3.7. And to have these go up in this amount only requires a global warming of about 0.3 or so. So what's all the noise about? I don't understand. Anyways, now there is another point of view. You can even say you can double CO2 and have no warming at all if it all went to extra rainfall. In other words, if the rainfall around the globe went up to 4.2%, you could balance out the surface with just rainfall. surface. Now you say you can't do that because this rainfall creates feedback loops, and the IPCC has assumed all these feedback loops are positive. But let's see. But anyways, evaporation, you see, is not related to radiation. It is in a long-term point of view, but day-to-day, month-to-month, season-to-season, it's not. You can have evaporation go up and down, not related to radiation. It's a bulk formula here. Now, this can go up and down. Our rainfall, our evaporation off the east coast of the continents and in the trades and so on, that varies independently of radiation. So we have the possibility to bring energy into the system or take it out by processes not related to radiation. Now, we've been looking a lot at the reanalysis data and the SCAP data. A lot of this, measuring albedo IR changes relative to rainfall differences as determined by the reanalysis data. And one of the great problems is this, you see, as rainfall goes up, we find, you see, you get deeper clouds, heavier rain, the mass goes up, you have large raindrops and so on, but you also have sinking on the side. Now, this is what really happens. So what we observe is the more deep convection, the more general net radiation, IR and albedo, the space you get, not the less. Now, the global models assume, the charting report of 79 and all that, that if you heat a little bit, the moisture goes up, you block more IR loss to space, and the whole thing gets warmer. There's a positive feedback. So they assume as rainfall gets more and more, they forget or don't handle properly this loop of sinking on the side that dries so much. So with more rainfall, they get less radiation to space. That's the crucial Achilles heel in the global warming. Now, in the upper troposphere, doesn't mean that as the globe warms, you get more vapor in the system. Sure, that happens. You get more rainfall. Rainfall doesn't relate necessarily to the vapor in the system. It's the upper tropospheric vapor that matters so much. Now, if you take a parcel from 200 millibars, 40,000 feet, bring it down to 30,000 feet, and start it out saturated at 200 millibars, the decrease of humidity of bringing that parcel adiabatically down 100 millibars, the humidity at 300 millibars is 14%. It goes down that much. We have such a gradient of saturated vapor in the upper troposphere. Now, we've done a lot of work looking at taking the months, the 10 months of highest and lowest rainfall, and looking a lot with the SCAP data and the reanalysis data. But we get, when you take higher and lower rain in different periods, different months, play around, we get upper tropospheric drying. And we get little upper tropospheric temperature change. So the big difference is the GCMs, you see, if you have enhanced evaporation, let's say 3 units, they have a feedback that these processes come in and you block more radiation, so you get an additional warming in addition to the condensation of, let's say, plus 4.5. We see from the odds you get an extra 3 units of evaporation, you get 3 units of condensation warming, but you get more flux out to space, and this pretty well balances this, and you don't get warming. And a hypothesis I have is the more rain, the more flux to space. The troposphere can't store energy. It can a few days or so, but over the long run can't store energy. So now let's look at the IPCC. This is the last report, report 4. They had water vapor feedback of 2 units of warming. Cloud feedback, roughly 1 unit. Albedo, positive, and they have a lapse rate cooling. That's because they put so much heat in the upper troposphere and the tropics. But they come out with a net effect of all feedbacks of about 2 degrees. That's wrong. That's just ain't right. We look at this data. Here's what the 1907 IPC models get. When we look at the data, we get nothing like it. Rather than get 2 units of feedback, we get -8 roughly. Crudely, it's in the noise level. So, what the IPC does, it warms. I agree with this. If you want to double it, you're going to get a warming about 1.1 degree or so. They give a feedback of 2.1 and get this warming. They all agree. All the models say roughly the same thing. And they're all wrong. What really happens is you get this, and we all agree. You get a blockage of CO2. Then there's a feedback here, and you're going to get only a warming of 0.3. Yes, CO2 will warm the globe, but it won't warm it much. And we certainly should not go to renewable energy because of this. Now, I want to show you how the lack of sensitivity of the globe is. Take the northern hemisphere, the whole thing. We've had the SCAT data up to 74. Here's the imbalance. Take the solar minus albedo minus the IR to space, and in the summer, you get tremendous excess radiation over the northern hemisphere, 40, 50 watts per square meter. How much does that warm? Very little. The troposphere in the northern hemisphere at most warms 10% of that or so. Where does all that excess energy go? Into the ocean. And in the, I'm going to jump ahead here, but here's a summer budget. In the whole northern hemisphere for 6 months, we averaged 284 units coming in, but the IR going out is only 239. There's an excess of 45. And at the surface, 198. Here you get much less. It goes into the ocean. In the winter, it goes opposite. You get much less coming in, much more going out as you draw energy from the ocean. So, okay, let's go forward here. Here's the best thing I've come up with, the observations from 30 to the pole. This fellow here and his colleagues. You see, going back to the time of Christ, we tended to have a little warming. General cooling, 350 years, warming, long cooling, and now we've been warming. Also, the same curve, if you look at all these little up and downs, if they're right. I plotted the maximum of these. You get about 60 units there. Anyways, okay. Only 3 minutes left. Okay, well, I'm concentrating on salt. The Atlantic is a very unique ocean because the rainfall is less than the evaporation. And that's due to the filling in of the Isthmus of Panama 2.5 million years ago, so it sequestered this whole thing. We have the buildup of salt here, and we have the flow through. This, you see, you have high latitudes where the salt content is quite high. You 5, 6 degrees or so. Temperature doesn't matter, the density is primarily salt. And we have relationships, nice temperature and salt. So I'm mainly concentrating on this MOC, or where you have, let's say, sinking up here, you have sinking in Antarctica, and you have rising motion in the southern oceans primarily. And we have periods when this circulation is stronger, we have more rising cold air here, but also in this situation, we get generally more rainfall that tends to cool. So you have rising cold water that cools, extra rainfall that cools, and we get periods where things are in steady state, periods when the circulation is stronger, and you get a net energy loss and cooling. And what? I got an hour left. Minus 58 minutes, right?
Well, now you have no time.
Okay. Well, okay. This will be my last slide. But what happens when this MOC is strong? We tend to have more blocking patterns. We tend to have the Atlantic has these more omega-type blocking patterns where you have more variation of weather here. And in general, the globe has, according to the reanalysis, more rain. Then we have these periods when the MOC is weaker, we have more zonal flow, we have less rain, and we have more El Niños in this period, less El Niños, hurricane activity is different, the whole thing. I don't have time to go through it, but this is the important, in my view, when you forget the orbital stuff. This is what causes the primary global temperature changes up and down. So yeah, radiation, ponder minimum, all that stuff may do a little bit. It's primarily in the noise level. This is the main driver.
Okay, a good moment to stop. For questions?
We have time for maybe one question.
Yeah.
I'm glad you all agree with this.
Yeah.
Just a simple question. Where does your data come from on the MOC being strong or weak? We've only monitored it for a few years.
Wait a minute, say that again, I didn't know.
Where does your data come from on the strength of the MOC? It's only been monitored for
Okay,
just a few
we have a
years.
proxy, we use, it's sort of a complicated thing. We use a North Atlantic sea surface temperature anomaly, the strength of the gyre and the westerly winds, and we make a proxy. No, nobody measures the amount of actual.
How do you know that it's...
Now, I forgot one thing. This is also related to the speed of the circulation of the Earth. If you look at the length of day and so on, there's a proxy you'll be able to use there.
So just a few, could the next speaker come up, please? Yeah, just a few clarification type questions, and hopefully we won't get into a full discussion yet. I think there was one more question.
Just a quick question. Your revision of the you're basically predicting that the IR has to go up.
As rainfall, yes.
Okay.
This will be the controversial point. See, they don't, this charting report of 79, when they said when it got warmer, the moisture, when the RH remains constant, therefore the Q goes up.
You should see
That just isn't right in the upper troposphere. Now, it may be right for the whole troposphere, but not the upper troposphere where the emission level is and you send that energy to space.
Anyway, that's the way of testing that. You're using data from that has a series in Kirby, so you can test your theory.
That's a good idea. So we'll move on to the next speaker.